We're starting video number 2, and video number 2 is about the photoelectric effect. I've drawn the diagram ahead of time, but so I expect you'll pause it or copy it out of your book or something similar. What we've got is just a simple circuit, so a variable voltage supply down here, which is, as it says, is variable, but can also be reversed to go the other way. Comes around, so at the moment this is the negative plate, this is the positive plate over here, so electrons should be attracted across. It's in a vacuum, and the vacuum is because you don't want the electrons being sucked up by any molecules of a gas, so you actually need to be a vacuum. And beams of light, should say more accurately, photons of light are coming in and striking the metal plate. So what is the photoelectric effect? It actually is when electrons are ejected from a metal by photons of light. Hence the photoelectric effect, because it's electrons being created by a light photon smashing into a metal surface. Now, everything from there on is simply about understanding the maths and the interchanges in all of this. So, stopping voltage. If the voltage is reversed, would help if that said voltage is reversed, some electrons still make it to the other plate, so the other metal plate. Some electrons still make it, and that means that they've actually gained electrons, so they must have energy from the photons. So what it means is that they're being actually sent across and being pushed backwards by a voltage. So they're actually being pushed away by a reverse voltage. What the stopping voltage means is the voltage required to stop the most energetic electron is the stopping voltage. Now, clearly that equals EK max. Stopping voltage VO equals EK max. And because it's a voltage, we know the energy of the electron because it's in electron volts. Now, threshold frequencies. We know from what we did in the first video that the energy of a photon depends on the frequency. So for each metal, there is a minimum frequency, which is therefore a minimum energy, for any electrons to be ejected. Okay, so I think sorry, didn't put that on the screen. I'll leave it on the screen for a few seconds and I'll turn over. We'll do a little bit about graphs. We will spend a lot of time in class trying to understand the graphs. Well, hopefully fully understanding the graphs. Graphs. This whole section is just absolutely full of graphs. Photocurrent versus voltage. So let's draw some graphs. We'll use the very basic colours for the backgrounds. Now the voltage goes backwards because we can actually reverse the voltage, and we know we need to reverse the voltage to stop the last electrons, so we expect it's going to go into the negative. So low intensity green, so that's very bright, low level green, and high intensity green. So very bright light. Intensity is just how much light you're getting. But because the energy depends on the frequency, and this green light all has the same frequency, then the most energetic electron for that metal is still exactly the same. Okay. Alternately, same graph again, and we do it with green light, and then we do it with any blue light. It doesn't really matter whether it's a light blue or a dark blue. The blue is going to hit further along because blue has a higher frequency, higher energy. Now, the last graph. This is the graph that you can absolutely guarantee will be examined. If we graph the stopping voltages which of course is EK max against frequency, and there's more of this to unpack in class, we get EK max, frequency, and what we do is we get a different graph for each different metal. So for example, this might be magnesium. Oops, I should have made it so that it hit the vertical axis a bit better than that. That was a pretty bad choice of angle. Never mind. I'll do this one over a lot further and we can use that for an example. Potassium. Okay, what I meant was I need to be able to dot down here till it actually strikes the vertical axis, the EK max axis, because we can read valuable things off all of the axes. So where it strikes here is F0 because that's the threshold frequency. That's the lowest frequency that an electron can come out. This is a really important quantity, not the negative value, but most textbooks will now tell you that that's W. The occasional book will probably tell you that there's another version than that can be called B, but they both have exactly the same meaning. W equals work function. That is the minimum energy to eject an electron. Now, we can see that it's a linear graph. It actually works out. This is what Einstein got his Nobel Prize for. Equals HF minus W. The gradient, because you know it's a y equals mx plus c, the gradient equals Planck's constant, so they all have the same slope. So all graphs in this have exactly the same gradient. Okay, now we will expand this a lot in class, and I'll also load you hopefully a very useful simulator that you can use on this as well. Okay, so that's the end of this one. We will unpack it in class, so don't panic if it doesn't make complete sense yet.